electron configurations and orbital diagrams, and I want to talk to you a little bit about some exceptions to the rule with that. Remember that electrons occupy distinct energy levels around the nucleus, and if we excite these electrons by giving them a source of energy, it's like throwing that pen from your bottom hand up to your top hand, or throwing it up to a kid standing higher on the ladder, then the moment that amount of energy that was required was a quantum, and the moment that we take that energy away, the electron falls back down in the form of a photon. So that photon is an energy packet. It's a short little burst of energy with a specific wavelength, and that wavelength corresponds to a specific color of light. So if I pass the light that is emitted through a spectrum, through a prism, I get a distinct emission spectrum. So this is examples of what you would see if I pass the light when we excite hydrogen, mercury, or neon through a prism. You'll notice that you get bars of light. You don't get a whole rainbow. Now this is called an emission spectrum. The picture of hydrogen down here at the bottom is an absorption spectrum. It's the same idea in the case of the absorption spectrum. The difference is that there was ambient light coming through, and so we see the interference patterns as black bars. But you'll notice that each bar, as it forms, is at the exact same wavelength, and these wavelengths are in nanometers, and they correspond to exact wavelengths for colored light. And this is what Bohr used to come up with his model and became the understanding that we use for quantum theory today. Now, when we do some of those transition metals, we actually get slightly different electron configurations than I'd expect. So, for example, let's consider chromium. Chromium, you fill in 1s2, 2s2, 2p6, 3s2, 3p6. Then you go to the fourth ring and fill in 4s2, and then you back up and fill in 3d for 4. Now, I have these arranged not in order of off-bar rule, but in order that you'd find them in the ring, so you can picture it. That this is my outermost shell, so I'd have my first shell, my second shell, my third shell, and my fourth shell of electrons, even though I know that these 4s electrons are filled in first. Copper is another one where I would expect, I'll do this one in red, that I'd fill in 1s for 2, 2s2, 2p6, 3s2, 3p6. And then I go and fill in 4s2, and then I backfill to fill 3d9. This would be what I would expect by following the rules I've given you. But anytime we do this and we end on D4 or D9, something interesting happens. It turns out that the D sublevel specifically, we would have the lowest possible energy available if the D subshell is half full or completely full, or, in fairness, completely empty. So when you end on D4 and D9, what it turns out that happens is something called electron promotion. We're going to move an electron. We'll take one of the electrons from that S sublevel and move it into the higher energy, promote it into the higher energy D sublevel. Now, it took work to do that. We said we put it into a higher energy level. But the resulting energy is lower, so it's willing to do this. If you've ever had to carry multiple bags of groceries into your house or up the stairs, and maybe you had 4 bags of groceries in one hand and 6 in the other, even though it took some work for you to transfer one of the bags over so that they were equal, it made it so much easier to carry that balanced load. You were willing to spend the energy to do it. It's the same thing that happens here. Anytime the last electron filled ends on D4 or D9, and we only have to promote one electron, okay, this works for one electron only, we will bump them into the higher energy level. So the proper electron configuration for chromium will actually be 4s1 and then 3d5. For copper, same thing happens. It had ended, remember, at 3d9. But once we've promoted the one electron, we now would have 4s1 and then 3d10. So remember when you are doing an electron configuration or an orbital diagram, and you find that you are one electron away from stability, that you must promote that electron from the 4s level to the higher energy 3d level. There is practice on electron configurations and orbital diagrams. Some of this is a continuation from the last lesson. Some of it is new. So there's questions at the end of chapter 5, and also worksheets 3 through 5, questions 1 through 10. Again, making sure that you're paying attention to any time where you might hit one of those discrepancies and be required to electron promote.